So this is the Python version of MATLAB. Sorry, the Python version of SLiCAP. And here you see a circuit built in LTSpice with SLiCAP components. And you see for SLiCAP, it is not important if it is a P or N device. That is in the model. You see the model is CMOS 18N, which is an N type. And this is in the library. And the width is also parameterized and the current also. You can use the parameter there. And here are the parameter definitions. Here I call for the library. And now this is, just assuming that the current ID is going there. It doesn't need operating point analysis because there are small signal parameters in this model linked to all these parameters I, L, and W as described by Binkley in his book with Designing with CMOS and the EKV model. And you can find those parameters in the library, and we'll go to the output later so you can see it. I just connect the same load resistance as I did in the LTSpice circuit. I also have a current driven and a very high resistance here. RS is 10 meg and 10K. I have the same type of device. So the models are different. LTSpice have a B-Sync model. Here is the EKV model and a small signal approximation of it only valid for the saturation region, but the results are quite nice. Let's say run all cells, and then it works. I'm always afraid that it happens, that it's just like bang, there's a bug. Now, this is the netlist. This is the parameters of the small signal model. It is the one MOSFET in the subcircuit XU1, and this is C drain in this one. So if you have more MOSFETs, you will have more subcircuits. These are the symbolic values, and these are the numeric values. You find them in the next table. If you do, this is the instruction that was also in MATLAB available, params to HTML, but it works a little bit different. If you put capital HTML, it displays it here, and you get all the parameters available in your circuit, and that's really a lot. But here you see inversion coefficient. 1, it's about 2. So we are working in strong inversion, but the critical inversion of this device, IC crit, is 126 with this long length, which means we are working in the quadratic region. And maybe you remember from the notebook, the Jupyter notebook with the devices, with a virtual machine, that we were indeed in the quadratic region of the curve. So that gives you a lot of information. Here you find the expression from Binkley, how you relate GM, the transconductance, to the operating current, the inversion coefficient and the critical inversion coefficient. I don't want to bother you with it. It's 1.5 milliamps per volt. If you calculate with LTSpice and with the Jupyter notebook, you find about 1.5, 1.6 milliamp per volt. So the models are quite good tracking. Also, FT is not bad at all. It says 1.5 gigahertz. I think it says the Jupyter notebook says 1.3 or 1.4 gigahertz. So the aim is that we are going to design first the small signal behavior of our amplifier using this. Then we are going to design the biasing, and then we can go to LTSpice because that one needs biasing, and then we should have more or less the same results as in SLiCAP. You don't need to use SLiCAP in Jupyter Notebook. You can also just make a Python file that does exactly the same. And people who don't have yet installed, I forgot to start it, sorry for that, who did not yet install the Python version of SLiCAP, they can use also the MATLAB version, because I have the same file there. Can I make it larger? I think it is. not possible with MATLAB. No, unfortunately, maybe now you have to look at very small screen. And this is also running. And here you are encouraged to go to Python. This one, that is the advantage of the new circuit, because you wait. This one takes 14.5 seconds. And this one, no, this one, it is also here. Takes 1.8 seconds. So if you want to do quick work, you better go to Python. And here you find the same characteristics as we did with LT-SPICE, but now with the EKV model. 2 poles and a 0, and the phase going from 180 degrees to minus 100 to minus 90, which is 270 span. The position of the 0 is a little bit, and the second pole is a little bit different, because the output capacitances have not been modeled very accurately. So that is why you find a little difference between the two models.